With this standard induction electric motor, it will be demonstrated how the performance of any electric motor system would be effectively doubled and the price halved, if simply converted to a patented electric motor circuit and control, or system architecture of best electric machine, or BEM, called SYNCHRO-SYM. SYNCHRO-SYM's transformational leap in price performance improvement is in addition to other price performance improving techniques that all electric motor manufacturers have strategically incorporated into the same century-old electric motor circuit and control architecture as their competitors, such as off-the-shelf or advanced materials, packaging, manufacturing, winding, and design optimizing techniques. To prepare the viewer for the demonstration, a short 13-minute overview of basic electric motor or generator components and design fundamentals will now necessarily follow. All rotating or linear electromagnetic motors and generators, traditionally called electric machines, are no different from this standard induction electric motor, which comprises 4 basic components. First component, the stator or stationary assembly, includes a balanced multiphase AC winding set that is excited with bidirectional multiphase AC electrical power directly through its terminals. Only a balanced multiphase AC winding set, which is independently excited with multiphase bidirectional power directly through its terminals, i.e., active winding set, produces a rotating magnetic field relative to its frame that does real work, by actively contributing electrical power to the electrical to mechanical, or electromechanical, conversion process. Second component, the rotor, or rotating assembly, which for this standard induction electric motor example, includes the so-called squirrel cage winding set. Without an independent, bidirectional, multi-phase electrical power connection to the terminals of the squirrel cage winding set, the cost, size, and electrical loss for a rotating electrical connection means are conveniently eliminated, but unlike the stator, the rotor cannot actively contribute electrical power to the electromechanical conversion process. Instead, the rotor squirrel cage winding power of the standard induction electric motor is a mutually inductive coupled component of the stator active winding power by a speed-based asynchronous movement or slip phenomenon, called slip induction. In effect, the rotor only passively participates in the electromechanical power conversion process by simply completing the magnetic circuit path across the air gap to establish the mutual air gap flux density. Without violating basic motor operating principles, the passive squirrel cage winding is often replaced with other means that also have no direct bidirectional multiphase AC electrical power connection for independently contributing real electrical power to the electromechanical conversion process, such as passive rotor saliencies, for the reluctance electric machine, passive rotor direct current or DC electromagnets, for the DC field wound synchronous electric machine, or passive rotor permanent magnets, that replace the DC electromagnets for the coveted permanent magnet synchronous electric machine. Note, it follows that the passive rotor consumes nearly half of the electric machine core real estate, as does the stator, with similar size, cost, electrical loss, or thermal dissipation as the stator, but unlike the stator, the passive rotor does not actively contribute additional electrical power to the electromechanical power conversion process. So, in effect, the passive rotor is worse than just wasted electric machine real estate. Third component, the air gap separating the rotor from the stator, where the speed-synchronized rotor and stator rotating magnetic field vectors superpose to establish the air gap flux density and to provide the electromechanical power conversion by pushing or pulling on the other's magnetic field in accordance with the electrical excitation frequency and voltage, directly applied to the terminals of the balanced multi-phase AC winding set of the stator. Fourth component, all other structural and mechanical components that do not actively contribute to the electromechanical power conversion process, but instead, provide air gap dimensional integrity under enormous magnetic and dynamic forces, such as the bearings, housings, end plates, and etc., provide thermal management, such as passive or active cooling, provide reduction of hysteresis and eddy losses, such as special electromagnetic and laminated materials, and provide high winding conductivity and voltage isolation, such as special insulated magnet wire and winding arrangements. Note, ironically, the structural and mechanical components add similar but significant size, cost, energy loss, thermal management, or design effort to any electric machine as does the electromagnetic design effort. As a fifth and increasing critical component of any electric machine system, electronic control of the current, voltage, and excitation frequency of the active winding set is now commonly used to at least implement practical operation of the electric machine, such as for the permanent magnet, reluctance, or doubly-fed electric machine, or to tune the performance of any electric machine between the dynamics of the application and the electrical environment. Note, the electronic controller, or drive, of any electric machine compounds the loss, cost, and size of the electric machine system, and as a result, should be equitably included in the overall price-performance calculation of any electric machine system. Still, it is expected that all electric machines will be electric machine systems in the near future because of significant improvement in application performance, such as varying the speed and torque to match the load, or ultra-high speed operation for higher electric machine power and specific density. All electric machines show the following basic design fundamentals. Similar electric machine power rating design means similar synchronous speed and torque design under similar voltage, current, and air gap flux density. Magnetomotive force, or MMF, of a winding is the scalar product of winding current and number of winding turns with winding magnetic flux directly proportional to MMF. In accordance with Faraday's law, the winding terminal voltage is proportional to the product of the number of winding turns and the time derivative of only the magnetic flux passing through the area of the winding, or magnetizing flux. Magnetizing flux is proportional to the energy product of a permanent magnet assembly or the magnetizing MMF of a winding or reluctance saliency assembly. In accordance to Lorentz law, torque is proportional to the cross product of the torque MMF vector, of the active winding set, and the magnetizing flux vector, of the air gap, and as a result, torque MMF is orthogonal to magnetizing flux, or magnetizing MMF. Total air gap magnetic flux is proportional to the vector sum of the torque MMF vector and the magnetizing flux vector. With all electric motor contestants optimally designed and without considering the extravagant expensive of rare earth permanent magnets, magnetizing MMF is the only cost, size, and loss distinction between permanent magnet electric machines and induction, or reluctance, electric machines. Since total MMF magnitude is the vector sum of the magnetizing MMF and torque MMF vectors, magnetizing MMF adds less than 4%, worst case, to the total MMF magnitude at full power, which is well within just the windage and material tolerance range between any electric machine design. Magnetizing MMF provides coveted field weakening capability for higher speed operation, for higher efficiency over broad speed range, and for electronic controller and insulation reliability. To leverage the attributes of field weakening, some permanent magnet electric machine systems ironically incorporate magnetizing MMF with all the associated loss, cost, and size that were the original argument for migrating to permanent magnet motors in the first place. The electrical excitation frequency versus speed of any electric machine must be in accordance to the so-called synchronous speed relation for useful torque production, which states, rotor speed and direction is directly proportional to the sum of the product of the stator multiphase winding excitation frequency and the inverse of the stator winding pole pair count, and the product of the rotor multiphase winding excitation frequency and the inverse of the rotor winding pole pair count, where speed and excitation frequency can be bipolar, i.e., positive or negative, and the excitation frequency would be zero for a rotor or stator without a multiphase winding set. Increasing winding current, or MMF, beyond the flux saturation limit of the magnetic core would no longer contribute to torque production or electromechanical power conversion, but instead, dramatically contributes to electrical loss. Furthermore, by effectively squeezing the flow of magnetic flux about the essential slots for containing the windings or permanent magnets, or for forming the rotor saliencies, flux saturation is particularly critical near the air gap by effectively increasing air gap depth and magnetic leakage as more of the high core permeability transitions to the permeability of air as a result of saturation. Therefore, chiefly constrained to stay within the same flux saturation limit of the same available core material used by all, any practical, optimally designed electric machine with a given power rating will necessarily show similar air gap flux density and effective air gap area, regardless of the magnetic energy product of rare earth permanent magnets or the even higher magnetic flux potential of a winding set with magnetizing MMF. It follows that an active winding set of any practical, optimally designed electric machine with a given power rating is constrained by similar air gap flux density and effective area, and as a result, will show similar cost, energy loss, size, thermal dissipation, power to volume, and power to weight. In conclusion, the basic electric machine components and fundamentals show all conventional electric machine circuit and control architectures, i.e., systems, of similar power rating, that are optimally designed with similar structural and mechanical components, will have similar air gap flux density, and similar effective air gap area, with similar size, cost, energy loss, efficiency, and thermal dissipation. Period. Therefore, with power density inversely proportional to speed, electronic control of conventional electric machines is becoming the practical means of achieving higher power density with ultra-high speed operation, of course, without considering the compounded size, cost, and loss associated with the necessary transmission for matching the high speed to the application. The futuristic alternative to achieving higher power density, higher specific density, and higher efficiency, or lower loss, is the superconductor electric machine system. By typically providing twice the air gap field strength as a conventional electric machine, regardless of core saturation, with an ultra-low resistive loss superconductor DC electromagnet of very high magnetizing mmF, the superconductor synchronous electric machine easily provides twice the power density and specific density with higher efficiency than conventional electric machines, but only by neglecting the formidable loss, cost, and size of ancillary enabling components for functional operation, such as electronic control, slipring assemblies, cryogenic refrigeration, electromagnetic shielding, reliability, maintainability, safety, and etc. With the anticipation of significant improvement of electric machine price performance, aggressive superconductor electric machine system research has continued with years of costly funding, but so far, with protracted success. With an understanding of the basic fundamentals and the future of electric machine systems, now here comes what we have been waiting for, the SYNCHRO-SYM magic. Simply retrofit the passive rotor element, such as the squirrel cage winding set of the standard induction electric motor, with a similar active balanced multiphase AC winding set as the stator, and replace the traditional multiphase slipring assembly and state-of-art electronic controller, such as any derivative of field-oriented control, with a brushless real-time emulation controller to sensorlessly and automatically assure synchronized speed and position, frequency and phase. Multiphase excitation power supplied directly to the rotor active winding set in order to eliminate any functional reliance on reluctance or slip induction with known speed regions of discontinuity and instability, such as about synchronous speed where slip induction becomes vague or ceases to exist. Replaced with a very compact, high-frequency, position-dependent flux rotating transformer of significantly higher power density inherently providing the analog processing for real-time emulation control, the multi-phase slip-ring assembly may well represent SYNCHRO-SYM's brushless real-time emulation controller assembly and accordingly, at least the following transformation leaps in price performance result. First transformational leap, the new retrofitted electric motor system becomes the only practical, brushless, multi-phase wound-rotor, doubly-fed, synchronous, electric machine system that contiguously provides symmetrically stable motoring, and generating, operation from subsynchronous to supersynchronous speeds, including about the unstable synchronous speed and zero regions. Note, practical operation of all other electric motors is only from subsynchronous to synchronous speed because of conventional state-of-art control instability, such as any derivative of field-oriented control. Second transformational leap, the new retrofitted electric motor system collectively shows the power of two active winding sets on the rotor and stator, respectively, or twice the rated power, in the same package as the original standard induction electric motor, but also, with the same materials, the same cost of materials, the same electrical loss, and the same thermal dissipation as the original standard induction electric motor, or system. Note, if considering the retrofit of a permanent magnet electric machine, the additional extravagant cost and real estate associated with cartel-controlled rare earth permanent magnets are conveniently eliminated, and thereby, leaving only relatively inexpensive copper and electrical steel as the remaining materials to consider. Third transformational leap, Since efficiency, electrical loss, cost, size, and thermal dissipation are always normalized to the power rating of any electric motor, the new electric motor with the collective power of two similarly rated active winding sets on the rotor and stator, respectively, reasonably evaluates to half the size and weight, half the electrical loss, half the cost, and half the thermal loss, per power rating, as the original standard induction electric motor, with the collective power of only one similarly rated active winding set. Fourth transformational leap, with contiguous and stable operation from subsynchronous to supersynchronous speeds, including about synchronous speeds, the new electric motor system shows twice the speed of any other electric machine for a given pole pair count, voltage, and excitation frequency of the active winding set, i.e., 7,200 rpm with 60 Hz and one pole pair, versus 3,600 rpm for the conventional electric machine system, which is a recognized characteristic associated with half the cost, half the electrical loss, twice the power density, and twice the specific density. Fifth transformational leap, in accordance with the physics of a truly dual-ported transformer circuit topology as provided by a fully electromagnetic electric machine system with the convenience of a balanced multi-phase copper wound rotor that is actively and stably enabled by brushless real-time emulation control, including about zero speed and synchronous speed, conservation of energy dictates that the air gap flux density of the new electric motor system remains constant with increasing current, or torque, on each side of the air gap beyond magnetizing MMF. As a result, peak startup torque can increase substantially above all other electric machines without leading to magnetic core saturation, or higher port voltage, such as 4 times the peak startup torque of a similarly rated induction, reluctance, permanent magnet, or even universal electric machine system. Note 1. In addition to providing twice the steady-state power density as all other electric machines, the new electric motor significantly increases peak startup torque potential, which conveniently alleviates the additional cost, size, loss, maintainability, and complexity of the common extraneous transmission for acceleration or deceleration in an electric propulsion application, such as an electric vehicle. Note 2. With the convenience of an inherent balanced multi-phase copper wound rotor, the new electric motor, again, provides higher efficiency, cooler running, and lower ownership cost than even the copper rotor expectations of the induction electric motor industry struggling for its introduction for at least meeting upcoming efficiency standards. Note 3. Unlike all other electric machines, the steady-state core flux density of the new electric motor can be designed closer to the saturation limit of the core without concern of reaching flux saturation with increasing torque current, which adds another level of lower cost, higher power density, and lower loss for the new electric motor. For all other electric machines with flux magnitude as the orthogonal vector sum of torque MMF and magnetizing MMF, the steady-state core flux density design must compensate for increasing flux magnitude leading to core saturation with increasing torque. Note 4. Shared between the rotor and stator active winding sets, magnetizing MMF of the new electric motor adds less than 2% to the total MMF magnitude at full power, worst case, if compared to the permanent magnet electric machine electromagnetic core, which is well within just the windage and material tolerance range between any electric machine design. SYNCHRO-SYM is the only practical, brushless, balanced multi-phase wound rotor, synchronous, doubly-fed electric machine system that is symmetrically stable while motoring and generating. Surprisingly, SYNCHRO-SYM's transformational improvement in price performance just demonstrated was already theoretically substantiated and published in the 1960s by academia, but the development of a practical synchronous doubly-fed electric machine system was essentially abandoned, after realizing the necessary enabling invention of a brushless, sensorless, and automatic control means to eliminate instability, particularly about zero or synchronous speed or during motoring, as only provided by SYNCHRO-SYM's brushless real-time emulation control or BRTEC, was beyond the technology of that time. SYNCHRO-SYM's doubling of price performance improvement over all other practical electric machine systems was verified by modeling and simulation with a computer-aided design tool specifically developed by BEM for the new dual-ported electric motor transformer circuit topology and brushless real-time emulation control architecture of SYNCHRO-SYM. Also, BEM complemented modeling and simulation verification of the SYNCHRO-SYM architecture with multiple stages of production prototyping for functional validation of the SYNCHRO-SYM architecture. Now, consider SYNCHRO-SYM versus the futuristic superconductor electric machine system. SYNCHRO-SYM is the only practical and stable electric machine system that replaces the wasted passive rotor found in all other electric machines, including the superconductor electric machine system, which reasonably consumes half of the real estate of the electric machine but without contributing to electromechanical power production, with an active rotor to effectively achieve similar power density, specific density, and efficiency as the superconductor field-wound synchronous electric machine system, but with proven off-the-shelf technology, and without the significant ancillary loss, cost, size, reliability, maintainability, and complexity of cryogenic support. Ironically, SYNCHRO-SYM's brushless real-time emulation controller, or BRTEC, can bring the traditional superconductor electric motor system closer to reality by at least conveniently relocating the superconductor DC field winding to the stator for simpler cryogenic support, for brushlessly relocating the active multiphase winding set to the rotor, for eliminating the slipring assembly, and for reducing costly harmonic heating as only provided by BRTEC with inherently pure multiphase sinusoidal drive waveforms for variable speed control. Much more beneficial than just the substantially higher flux density provided by passive DC superconductor electromagnets, superconductor alternating current, or AC, multiphase winding sets, which also provide significantly lower overall electrical loss, are being aggressively researched, and when practical, a brushless, fully electromagnetic AC machine, as only provided by SYNCHRO-SYM, would be the obvious choice for the AC superconductor electric machine application, particularly after realizing that today, the induction electric motor, with a passive rotor, is industry's best consideration for implementing the fully electromagnet AC superconductor electric motor. As the only symmetrical, fully electromagnetic architecture, SYNCHRO-SYM provides many more transformational leaps in price performance that are too numerous to list here. So BEM invites you to visit our website at bestelectricmachine.com to learn more about SYNCHRO-SYM technologies or to submit your questions, comments, suggestions, or requests. If you like the simplicity and innovation of SYNCHRO-SYM, Best Electric Machine, or BEM, has also leveraged several additional patents, such as the only 3D printer, called motor printer, for laminated, object manufacturing of the preferred adjustable air gap, axial flux electric machines or the smart grid, high-frequency, high-power transformer, which BEM is developing to democratize the high-speed, just-in-time, low-waste, universal additive manufacture of axial flux electric machine cores. With integral frame and bearing bezel assembly, and for the in-house, additive manufacture of the axial flux form of SYNCHRO-SYM, which includes an integral high-frequency, high-power transformer. In a small footprint, motor printer builds from relatively inexpensive pre-processed, high-performance optimized electrical steels, such as amorphous metal ribbon, and off-the-shelf structural materials, such as aluminum, steel, or composite bar stock, without adversely affecting their coveted but delicate pre-processed magnetic or structural performance properties, which is very different from the few contemporary ongoing 3D printing approaches for manufacturing electric machines, that are still in heavily funded research under guarded expectations of actual success, but worse, these 3D printing approaches utilize pre-processed materials with more stringently controlled removal waste that are specifically manufactured and optimized for compatibility and consistency with the 3D printer itself, instead of for the electric machine core and frame assembly. With motor printer, Best Electric Machine again distinguishes itself from all other electric machine manufacturers with innovative manufacturing tooling, instead of simply applying better available packaging techniques and performance materials for price-performance enhancement of the same traditional century-old electric machine circuit and control architecture. Furthermore, highly reliable, adjustable air gap, axial flux, amorphous metal transformer cores provide even flux distribution and isolated, high-frequency, high-power, low-loss, direct AC to AC conversion, with SYNCHRO-SYM technologies, for the future of smart grid power distribution and conversion, instead of traditional method of DC link stage conversion with bulky, expensive, and delicate capacitors.